Right, so hi Andrew, and sorry about that bit of a delay. So what I thought of doing today, because I didn't have quite time to set up for the solubility to start that, we just do a final lesson on the spectroscopy of putting it all together. And quite frankly, because you've attended all these lessons, you would be pretty much be able to go straight into the teacher-marked assignment and then the assessment task. Because we've pretty much covered everything. This, what I'm going to be doing today, is needed for merit and for excellence. For merit, you've got to tie information from 2 spectra together, and from excellence, you've got to tie for 3 spectra together. Okay, any questions before we start? No. Okay, right, so what I've got there on the screen is what you're given in the task. So you don't have to learn things off by heart. You can always refer to it, and you can tear it out from the back so you don't have to keep on flipping through pages. Now remember, the fragment structures, I don't give you every single possible one. These are just sort of examples. Some of these may come up, others you may have to work out. So let's work through a few examples. So some of these we did last time, but I thought it's good to revise. So there's 2 parts to this, is working out the elements and the functional groups present, and then once you've worked out your molecular formula, then the second part is to work out what the actual isomer would be. So let's quickly go through the functional groups present and absent, because as I say, we did do this last time as well. So the first one is, remember, you hear the 3 spectra, and you look at them and work out, first of all, what elements are present and absent, and then the functional groups. So the good place to start is always with the mass spec and the molecular ion, because the molecular ion tells you a number of things. Do you remember what they tell you in terms of elements present or absent? So if you saw that, and it's a molecular mass, or the molecular ion is 74, so it's an even number, what does that even number tell you? There's no nitrogen present. Strictly speaking, there's no odd number of nitrogens present, because obviously if you have 2 nitrogens, you'll get an even number, but I would never do that to you. So there's no odd number of nitrogens present, no nitrogen present, and then you look also at the peaks here, and you see, are there 2 peaks 2 units apart? I can see you typing. So are there 2 peaks 2 units apart in either a 3:1 ratio or a 1:1 ratio? And correct, there are no isotopes, but in particular what elements we're looking at. So there's no chlorine and no bromine. Correct. Okay, so we can see that it's even with no nitrogen, no chlorine, no bromine. And remember, for merit and excellence, try and tie in the other one, so we can see in this part of the fingerprint we don't get any of those halogen peaks, the CX peaks, either CCl or CBr. There's no sort of strong peaks over here. We can see that there's oxygen present because of this OH group over here. And there's no strong fingerprint region, strong finger-like peak over here. That peak over there is by 1500, so it's in the fingerprint region. So we know there's no carbonyl, so we've only got 1 oxygen present. We don't have another oxygen present. I'm not going to give you a molecule that has 2 OH groups. I won't ever give you multiples, because this is only level 3. So we can say we've got carbon and oxygen and hydrogen present. The carbon and hydrogen we know from 2 places. Well, the carbon is, remember, this is an alkyl group in the IR, and remember this is a carbon NMR, so if we have any peaks in the carbon NMR, we have carbon peaks present. We've got at least 3 carbon atoms present. Okay, so we've got carbon, we've got hydrogen, we've got an oxygen, and we don't have nitrogen, bromine, or chlorine. So we then work out our formula. Okay, this is just, we're going to quickly flip through here. We've already explained why we don't have those and double up. Also, we can't really see if we've got an NH there. We know there's no CN over there. So remember, right on the spectra, try and get as much information. We know we've got an alkyl, so it's CH, and there's also in this region, round about 30 and below, it tends to be the CH2, CH3. So we know we've got CH there as well, and we know we've got an OH. This strong peak round about the 1000, it's sort of around here, is the carbon attached to a hydroxyl group. This is so when you do a breathalyzer test for the police, it's actually a little infrared thing, and it looks specifically for this peak for ethanol, because it's ethanol that you drink in alcohol. So that is that CO stretch over there. So we can work out, and then of course always check where else you could find it, and we have got a carbon attached to an oxygen, because if you look at your NMR table that's showing, it's on a different screen for me, but you should see it in the lesson. If you look for the CO peak round about halfway down, that's carbon 13C NMR correlation table, you'll see it's between 40 and 80. So it's carbon CO, or carbon attached to an oxygen, is sort of in this area. Right, and another way we can suggest it could be an OH is, remember, an OH, a COOH, or an NH tends to lose hydrogen very easily. So that's where this little peak is supporting. So if you've got all that down, you pretty much got excellence, actually, although you need more from the formula. And then just a few more negatives. Remember, you do the negatives as well as the positives. So molecular mass of 74, we've got a minimum of 3 carbon atoms from the NMR, we've got an oxygen present. So if we try and add up the molecular mass to get to 74, 16 of that mass is taken off because of that one oxygen. So the carbon and hydrogen makes it about 58, and we can't have just 3 carbon atoms and round about 22 hydrogens. It won't fit. So we need more carbons, and if we have 4 carbon atoms, it will go to 48, which makes it about round about 10. Yep, so it could be a secondary alcohol. We'll just have a quick look when we get, because I double these up again. And then remember, also check your formula. If you come up with a formula, check if it matches those saturation formula I gave you. So we know, for instance, we don't have a double bond here for the C double bond C or the C double bond O. So this matches it, because remember, if it's saturated, it's CnH2n plus 2. So this is 4 times 2 is 8 plus 2 is 10. Remember, oxygen doesn't affect that ratio. Okay, so let's do this one now. So what we do straight away, remember, is go for that. It's even, so do I have nitrogen present? Probably not. And as I say, I'll only ever give you a single one, so it's not. Do you see an isotopic ratio for either chlorine or bromine? No, because it's not too, there is a little peak there at 117, but that is from the carbon 13 isotopic ratio. Remember, if it's round about 1/50th, 1/60th the size of that tall peak, then that's from carbon-13. So we've explained that, and remember, check from everywhere else from the other spectra to support why we don't have chlorine, bromine or nitrogen. And there we get from the NMR. Then we've got carbons and hydrogens. We can support that with the carbon-13 NMR. And then now we're looking at functional groups. We can see there's no double bonds for carbon-carbon double bond, but we do have this carbonyl strong finger-like peak. So if you look at where it is, it's between it's around about 1730. So it could be an ester, it could be an aldehyde, it could be a carboxylic acid from where this peak is. So I'm trying to find my, so that says it could be those, but why is it not a carboxylic acid? And I'm tracing what you would expect to see if it was a carboxylic acid. What would you expect to see for a carboxylic acid? You don't see this big triangle centered over the 3000 mark. So it's not an acid, and you write that down because we don't see that. We've said it could be an ester, aldehyde or ketone or carboxylic acid just based on the position of this. But from this peak over here, we can say it's not an aldehyde and it's not a ketone. Why can we say that? And again, you can just look at that NMR table. That's, you should be able to see. It's not downfield enough. An aldehyde or ketone will be round about 200 or further down. So this basically says we have an ester. We know it's not an amide, because A, we don't have nitrogen, and B, remember, an amide would come further down, below 1700, and we know it's not an acyl chloride, because A, we don't have chlorine from this, and B, we don't, the acyl chloride peak is always, remember, closer to 1800, whereas this one's below 1750. So we know we've got an ester, and now we just say also what, give reasons of what's not there, okay, and okay, I've done lots of things here. So remember, the CO peak is more downfield, whereas a carbon attached to a carbonyl also shifts a bit further down from the others, whereas those are just the alkyl peaks. And remember, the methyl is always the most upfield. So now we just work through it. We look at the number of carbon environments. We know we've got 2 oxygens present because an ester, remember, has 2 oxygens. One is a carbonyl oxygen, one is from the alcohol. So that gives a mass of 32. And now we just work out what the rest could be. Now I do see you typing, so I will check what you've written there. Okay, yes, it's got 6 carbons, and notice it follows the CnH2n. 6 times 2 is 12, so we've got 1 double bond there, and we know it's a double bond because we can see it there, and we can see it there, our double bond. Right, here's another one. So remember, go hone in on that, and notice we've got a little isotopic peak there, and we've also lost a hydrogen. Now remember, if we lose a hydrogen, it's most probably OH, COOH, or NH. One of those 3. Could be others, but those are the most common ones. So go for it. 87, odd number. So we know it's a nitrogen. So that loss of hydrogen there it's lost from the NH. And we follow up. We've got a secondary peak there. Okay, I think you were saying that. We've also got this funny, if we've got a nitrogen, we often get this NH wag. This is the NH stretch, but there's often a little funny thing down here. And we can also check with our NMR. We've got something quite downfield. It's not O8, CO tends to be further down, whereas CN not quite so further down, because remember oxygen is more electronegative, so it makes it more de-shielded. Right, and then if we've got a secondary NH, we do expect to see 2 carbon peaks, unless of course that molecule is totally symmetrical around that secondary carbon that has the NH2 attached. Oh, sorry, if it's totally symmetrical around that nitrogen. So in other words, if you've got a, say, a CH3CH2, an ethyl group, 2 of them attached to that nitrogen, it would be in the same environment. Okay, and now we go through what's not present, so make sure you do that as well. So I'm just clicking on all those. And now we go with the formula, and it's the same thing. We look at the 5 carbon environments. We know we've got a nitrogen present, so we have to take that mass off. So we've got the carbon and hydrogens make up 73 mass. We've got 5 carbons from the NMR, that's minimum. So that sort of makes a suitable formula. So we, each carbon atom is, we know, is in a different environment here. Does it match our saturation? Because remember, we've got no double bonds here, no double bonds there, and the formula for if we have a nitrogen present is CnH2n plus 3. Yes, so in the teacher marked assignment we do the structure as well. So we will come to that in this lesson. So let's do this one very quickly again. There's your peak, okay, 78. Now, can you see there's an isotopic ratio of 3:1. It's always the lower one that is the bigger peak. That's just the way the isotopes work. The lower mass one seems to be more stable. So carbon 12 is more stable. There's more of carbon 12 than carbon 13. There's more of chlorine 35 than chlorine 37. Or there's more of bromine 79 than bromine 81. So you'll always find the main peak is the lower one and the isotopic peak is upfield. Okay, so now we just go through it. We can see we've got chlorine. It matches what we've got in the fingerprint region. It sort of shows that you can look at that carbon 13 correlation table where the CCl is between 35 and 80. It's a very broad range, but it's around about 40 usually. It just depends on what else is there. And it is sort of around about 40, so that's the CCl one. And then we have to say what's not there, what is there. So write on the spectra to say what's not there. And then we work through the same sort of thing. And as I say, I've done that in the previous lesson. So we get to that formula. It matches a saturation because remember a chlorine is the same as a hydrogen. So it's the same as C3H8 because it's 7 plus the Cl makes it 8. So it matches a saturation of Cn2n plus 2. Any questions so far? I know I'm going through it quite quickly because I have done this last time. No. Okay. So here we've got now, it's quite condensed, so it looks as though that's only 1 unit apart, but can you see there's a tiny little thing in the middle there? So that's 2 units apart of a similar size. So it's Br present, correct. And you can see that same thing over here. So here we've lost probably, it's 43 being lost, and 43 is normally that propyl group. Because remember, methyl is 15, ethyl is 29, and the propyl group is around about 43. And we have a double bond, correct, C double bond O. So let's just sort of go through it all. It's very good to go systematically. So when you identify something in one, check that you've got it in the others. Okay, or if you identify something absent in the one, check that it's absent in the others. And so we've said there's no nitrogen, and now we're saying we've got an alkyl CH, so where would the CHs be? That shows I've got carbon because I've got 3 carbon peaks, and this area shows I must have hydrogens because they're the alkyl area. And I've got no CC double bond, but I do have a CO double bond. And I don't have an acyl chloride, and I don't have an amide. And we know we don't have an amide for 2 reasons: no nitrogen from the molecular ion, and it's not below 1700, and we know it's not an acyl chloride, again from the mass spectra, but also it's not close to 1800. So we now work out I must have 2 functional groups present, because that tells me it's an aldehyde or ketone. Okay, anything sort of 200 and above. And I know I've got a bromine present. So if my molecular ion is 150, so notice it's always the lower one. Don't say 152, it's 150. And I've got 4 carbon environments, 1, 2, 3, 4. So 1 Br present. I've got an oxygen present because of this carbonyl. So I can work out what's available for the carbon and the hydrogen by subtracting those figures, and I get 55, which gives me a reasonable formula of C4H7OBr. Okay, and remember the Br is the same as adding on a hydrogen, so it's C4H8, the Cn H2n, I've got 1 double bond. And I think this is the last one for the elements and functional groups present. So it's again, we look over here, we've got 1 at 80, and we've got 1 at 81. Sorry, it's actually a bit tricky to see because we can't see. But that is not bromine. Give me a few reasons why this is not bromine. So it looks as though they're more or less the same size, but there's a number of reasons why it won't be bromine. The molecular weight. Remember, bromine is 79 and 81, so if I add a carbon to that, it's going to make it at least in the 90s. So we know it's not bromine. Also with bromine, the lower peak is always slightly higher than the higher peak, or the one that's further up. And in this case, it's the other way around. The one that's further up is slightly higher than the one that's further down. And then you're quite correct, these are only 1 unit apart, and for bromine it should be 2 units apart. So look carefully, don't be fooled, think, oh, 2 peaks similar in size, bromine, because there's a number of reasons. And of course we know there's nothing here for those CBr stretches, so we haven't got it there. Right, so it's 86, okay, and you can explain, I'm not going to spend too much time on the Cl and the N because I think we've done that by now. So we've proved that we've got C and H's present. We've got a double bond, C double bond C present, but no C double bond O. And this NMR tells you very clearly that it's a double bond, and we've got an alcohol. Very well done. So I haven't got quite to that end yet, so I haven't got it there, but you've already picked it up. Now notice this sort of fairly wide spacing, so they're quite different, the 2 carbons of the double bond. The one that's sort of round about 110, so this one's 115, will always be a CH2. It won't be a substituted one. It won't be a CRH. This one at 140 is probably a CRH, because if the carbon double bond has got 2 other carbons attached, it tends to be closer to 160. It tends to be more over here. So we've most probably got a terminal alkene where the second carbon in from the chain has only got one other carbon attached to it. So it already can tell you quite a bit about the structure. And then, as you said, if we go now further up, because I always start with the alkyl, then I go one up, and now we've got an OH, and we can show that is supported in the NMR by, remember, a CO is around about 60 to 80, and there we've got one there. And we know we don't have a carbonyl in either of these areas. So point that out. Now we just work out our formula in the normal way, and we get something. Do we have a saturated or an unsaturated ratio there? What does that match? C5H10. One double bond, correct. Okay, and then as I say, that OH, can you see we've got a little peak below that loss of hydrogen? Right, so what we want to do is we're going to do the same 6 examples, but we're now going to do the next step where we work out possible isomers. So remember, in this particular one we had that OH but without any double bonds present. So we've got to work out what we could draw. So C4H10O. The easiest way is to draw 4 carbons in a row, put an OH on the first one, and put the rest of the hydrogens on. So here are some examples. Can you see 4 carbons in a row with an OH on, 4 carbons in a row? I've moved the OH on a bit further. If I move this OH onto this carbon, will I get a different isomer? So this is now thinking of the work at 3. No, because a good way is to work out the name. So this is butane 1-ol. This is butane 2-ol. I count from 1, 2. If I move the OH onto here, I'd start counting from the left-hand side. So it's still butane 2-ol. So I can't move the OH any further because I'm just going to get the same molecule again that I've drawn, the same isomer. So what I do now is I just make 3 carbons in a row, put an OH on the end, and then put on the 4th carbon as a methyl. And so I've got 4 possible isomers I could draw for that formula. Now you've got to work out which one is probably the right one. And this is where the fragments are very useful. Okay. So, first of all, actually look at the NMR, the number of carbon environments. I've colored them differently for the different carbon environments. So, in butane 1-ol, I've got 4 carbon environments. Can it be butane 4-ol, sorry, butane 1-ol based on the carbon NMR? No, because I've only got 3 carbon environments. How many carbon environments do you think butane 2-ol has got? So to work out if it's got the same carbon environment, you always state exactly what the 4 groups on each carbon are. And if they're identical, then, or the alkenes can be a bit funny that way, but if they're identical, then they are they'll be the same environment. But if they're different, then they've got different environments. So you're right, it's got 4 carbon environments, that one's got 4 carbon environments, and you're listing them all. Now this one has got 3 carbon environments, because if I looked at this one's got 2 hydrogens, an OH, and an isopropyl, or a C3H9 fragment. The blue one has got this methyl hydroxy group and 2 methyl groups and a hydrogen. So it's different to the red one. The 2 pink ones are identical because they've got 3 hydrogens and this blue-red thing on it. So both of them have the same, so those on the same environment. So that will match this. If I look at this one, how many environments does this one have? The one that's on the right. Just 2, correct. So all those methyl groups are in the same environment there, so we know without even going into a fragment that it's this one. But for excellence, show your fragments. You should be able to do that. So you should be able to work out a fragment based on the tallest peak. That's called the base peak. And if I remove, in other words, if I cut it over here between the blue and the red, I get left with a fragment here. Don't forget to put the positive charge on, because it's the positive charge that makes it get picked up. Okay, it measures the mass to charge ratio, so it must be charged, and that will add up to 43. 3 carbons 12 plus 7 hydrogens is 43. Draw out the structures just so you can make sure you don't make a mistake in counting the hydrogen atoms. It's a secondary carbocation, so it's fairly stable, so that's why you've got so much of it. If you've done that, you've got excellence. Okay. Any questions before I go on? No. Okay. Here's another one. If you, as I said, try and do the base peak, but if you can't think of anything at the base peak, then find another one that could show. So for instance, this little one over here shows the loss of hydrogens. If you drew that, where you chopped a hydrogen, sorry, if you took the hydrogen off here and you made it O+, okay, then that would still shows you've understood it. And here's the one, the peak at 59, that's this one over here. Okay, there's 60, so this peak at 59. And that's where I've lost a methyl group. So if there's a difference of 15 from 74 to 59, it's normally a loss of a methyl group. And there you've lost a methyl group, and it's also a secondary carbocation. Right. Let's look at this one. We worked out when we did the functional groups and so on that the formula would be C6H12O2, and we know it's an ester. So really there's actually quite a few we could draw. So we could draw 5 carbons in a row and 1 carbon on the other side. So as though it came from methanol. That's got lots of different environments. 1, 2, 3, 4, 5, 6, and we've only got 5. So we could play around quite a bit. What you need to do is sort of like have 2 methyl groups on either this end or that end. Now, if you get given a complicated one, you do not have to get the exact isomer. So don't think, how am I going to get the exact isomer? But as long as you can support your structure, we will accept it if it's a complicated one. Okay, so there you've got something that's got 5 carbon environments. So you could have also made sort of like 2 ethyl groups on this side. So in other words, taken a methyl and put it there, and just had an ethyl on this side. So here's an example of that. 5 carbon environments. So it could be the second option or it could be the third option. And here's some more options where I've 1, 2, 3, 4, 5, 6. Yeah, I've gone back to a methyl there and I've done the 2 ethyls. So there again, there's 5 carbon environments. Do you think you would be able to draw some of those isomers? It's just playing around with them. With practice, yep. And as I say, you've got lots of time in the task. So, you know, use as much time. I know we've said an hour, but a lot of students have gone 2 hours with it. So use as much time as you need to just sketch out something. Right, there'd be a lot more isomers I could draw, but we're just going to stick with those. And now we need to try and explain to see which one of these, sort of an extra backup that I could choose between the second, the third, or the fourth one. Because from the NMR, we know it's not the first one, it's got to be one of the other 3. So a base peak at 43, we get from all of them. Okay, so all of them would give you a base peak of 43, because the first one, that fragment there, will give you 43. With this one, this fragment here, if it breaks between the O and the C, it would give you 43, yes. Here, this one over here, but if it breaks between the pink and the green, would give you 43, and the same thing there. So as you quite said, the isopropyl group. You've obviously at university, so you know the isopropyl name. Others at level 3 wouldn't have really come across that. Okay, so the base peak doesn't really help, and you must sort of try and explain why the one would work with the other one. So this peak at 71 is quite definitive, because you could get that with number 3, but you can't really get it with any of the other ones. So if you try chopping it sort of over here, this doesn't make 73. If you chop it over there, that doesn't make 73. And the same thing obviously for this one. Over here it doesn't. So if we need 4 carbons, 7 hydrogens and an oxygen. So 1, 2, 3, 4. We need 1 oxygen and 7 hydrogens. Possible psyllium ion. Have I got there? 1, 2, 3, 4. Oh, 1. Oh, yes. So if it gets chopped over there between the pink carbon and the oxygen, we can land up with a peak of 71. Notice we don't get that with here because we don't have 4 carbons there, and that one has got 5 carbons, so we can't get it there. So you'll have to just sit and count and add up and see where does it chop. So in other words, you work out what could make up 71 and then try and chop the molecule and see what would make up to that. And in this case, it's 4 carbons, 7 hydrogens and 1 oxygen. Sometimes, because of funny rearrangements, you can't ever make it match a peak. So if you find that you can't match that particular peak, forget it and move to another peak. But normally the big peaks are okay. It's the little ones where you can get sort of rearrangements. But the base peak you should be able to explain, and perhaps another big peak. The ones down here often have been broken up and rearranged in lots of different ways. So I wouldn't go too far down. Okay, so it would be, this is the one. If you chose any of the other ones and you had some sort of evidence using the mass spec and the NMR, it would still be acceptable, because this is a complicated one. There I'm just showing you where the different fragments come from. Okay, any questions? No. Okay, right, now what I've shown here, so this was number 3. This is the mass spec of this one over here. So that's why I've got a 2 here. It's from that one. Can you see it's a bit different? It still has a peak at 43, but it's got the base peak is over there, and it doesn't have anything at 71, because remember we said we can't get anything at 71, but it has got something at 74. And this one, the mass spec looks like this. So again, there is still something at 43. We don't have anything at 71, but our base peak is this one over here. You could perhaps even try and work out, just for fun, where would we split these to get a peak at 70, what's it, 75, I think that is, 74. It'll be the same one sort of as there. Okay, right, so here's now we've got a nitrogen present, and that's our formula. So we draw the possible isomers. So 5 carbons in a row. We know it is not saturated. Sorry, not unsaturated. It's saturated. There are no double bonds. So 5 carbons in a row. Oh, what I've done is not 5 carbons in a row because I know it's a secondary. So I can't have the nitrogen right at the end as a terminal NH2 group. We know it's got to be NH. So I've done 4 carbons in a row in and then the methyl group. So that's 1. And how many carbon environments have I got? 5. And does it match the number of environments over here? Yes. So it is a possible structure. And now I've tried another one, and that's also 5 environments. I do another one, and that's now not 5 environments because the 2 methyl groups have got the same 4 identical groups on them. 3 hydrogens and then this big thing over here. So that is not a possible structure because it doesn't match the NMR. Now, there could be others you could draw, and you can play around. I just don't want to go through every single one. If you've got a few that match, then see if it works with the base peak or anything else. Now, that little peak over there, the loss of hydrogen, is when just simply this hydrogen gets chopped off. Okay, so if that, when you put a plus, you take the hydrogen away and you put a plus on the nitrogen, then you've got a fragment for that one over there. So our base peak at 58, it's possible with number 2, this one over here. It's not possible with number 1. And I'm just saying, we've got to lose an ethyl. So if I go from 87 down to 58, that difference is 29, and 29 is always an ethyl. CH3, CH2. Do I have an ethyl group in the second one? I do, because I've got that I can get chopped off. Now I could get an ethyl chopped off by removing the yellow and the green, because that's also an ethyl group. But if I do that, my cation on the purple carbon, is that a primary, a secondary, or a tertiary? It's a primary. Whereas if I chop this off over here, the nitrogen becomes positive. Now, what do you know about a positive on a nitrogen? Is it stable or unstable? I mean, all cations, of course, are unstable, but there's degrees of it's stable. So, because it's such a tall peak, and that most of it has formed this one and very little has formed anything else, all amines, by the way, will have this peak at 30. It's a rearrangement, so don't bother ever explaining that peak at 30. But if you see a peak at 30, for an amine, I mean, it's another bit of evidence that you've got an amine. Some amides also have a peak of at 30, but don't bother explaining it. Right, so that is, we can work out at structure number 2 to explain that peak over there. And that gives the NMR for that. So the 2 downfield peaks are the carbons attached to the nitrogen, and this one is closer to the nitrogen, so it's further downfield. That one is further away from the nitrogen, so it's further upfield. Remember, the electronegativity is sort of felt through 3 bonds, so this carbon feels it a bit stronger than the one that's further away. Any questions on this one before we move on? No. Okay, and that's if you wanted to see number 1. You can see what's happened with just about everything comes on 44. Okay, so that's where it's chopped. I'll have to work out what 44 was. I think it's if it gets chopped there, but just if you wanted to, you could work out what it is. Right, so we've got 3 left to do, 4, 5, and 6. So here we've got a chlorine, a haloalkane, and there's no double bonds anywhere. So this one's in a way the easiest because there's very few isomers you can draw. 3 carbons in a row. Those are all different environments, which matches our NMR. That one has got 2 environments because those red methyl groups have the same 4 groups attached to them. So they're the same environment, and you would have only seen 2 peaks if you had this one. And there's no other isomer you could draw. Those are the only 2 isomers possible with that formula. And so the easiest one with chlorine and bromine is chlorine and bromine gets knocked off very easily. So you can see I have very little with chlorine in it, most of it where the chlorine has been knocked off. So here there's been a loss of 15 where a methyl has been knocked off, that green methyl to form this peak over here, but that one is the chlorine has been knocked off. Now that is a possible structure for 1 and 2, but as I say, we know it's not 2 because of the NMR. So there we've got that. The base... Oh, that shouldn't have been base peak at 49. I'm trying to work out... I think I've... Sorry, that's a mistake. I didn't quite work things out there. So... okay. I didn't put my order in correctly, and that is actually a mistake. So if I was trying to do this, if I've lost a methyl, then you can get that strong peak there at 43. But that's just for the chlorine and a carbon. Okay. Any questions before I move on to the next one? No. Okay. So here we've got the formula that we've already worked out. Now we know we've got a carbonyl, so our isomer must have a carbonyl in it. It must have a bromine in it. Okay, you won't get an acyl bromide because that's not part of the standard. If you had a chloride, an acyl chloride is possible, but you wouldn't get an acyl bromide. So you need to have a carbonyl and a bromine. So start off with a carbonyl and add the bromine, move it along. Okay, I put it on the first one, there it's on the second one, there it's on the third one. Then I've tried putting the carbonyl further in. Okay, if I move the carbonyl to that one, if I've got 4 carbons in a row, you start simply counting from the other end. So I can't move the carbonyl more than on the end or on the second carbon, because there's only 4 carbons in a row. Is that understandable? Why you would only have those 2 possible positions for a carbonyl? So it's, yep, okay. Because as it moves further on, if you try and draw the carbonyl there, you'd simply count from the other end. So you could play around and just move the bromines along, and so those are some possible isomers you can draw. They're all 4 carbon environments, if you checked each one, and we've got 4 peaks, so all of them would match. So you've got to now try and work out what it could possibly be. The base peak at 43. So you can see we've lost something here to get we haven't lost a bromine there, but to get all the way down, we have lost the bromine as well as another carbon. So there's 4 carbons there. So if I've got 3 carbons plus 7 hydrogens, so like an isopropyl, a CH3, CH2, CH2, or CH3, CH, CH3, that's the isopropyl one that I gave the second. If my compound has that, that could give rise to this peak at 43. Another way is if I had 2 carbons, my oxygen and some hydrogens. So in other words, if I've got a carbonyl, so where could I get a carbonyl? If I look at this one over here and I chop it between the carbonyl and this carbon with a bromine, and I put a positive charge on the carbonyl, can you see that would add up to 43? 2 times 12 plus 3 plus 16 gives me 43. So that's a good one. This would also give me the same. None of the others, I can't chop this. Well, I suppose this one I could chop over here. That gives me 2 carbons, 3 hydrogens and an oxygen. But if I do that, what sort of carbon have I got? A primary, secondary or tertiary? Primary, and that's less stable than if the positive charge was on the carbonyl. And it can't be on this one over here because I've got a bromine attached, so it brings up the weight a lot. And here it's the same problem as I've got there. I've got a primary carbon. And by having such an enormously tall peak and hardly anything of the rest, I know that that fragment's pretty stable, so it's most probably not going to be primary. So there's your stabilized one. So it's either 5 or 6. And you can try and work out so that 107 peak, that's this one over here, it's again 5 or 6. So this would be a case if you would have picked either of those, would have been acceptable for excellence without a problem. Okay, and that, although it looks like an aldehyde because it's closer to 200, in this particular case, because it's also influenced by the bromine, it's not quite as far down for a ketone as what you would expect. So normally if it's closer to 200 it's an aldehyde, but it could also be a ketone. If you look at that NMR table, you'll notice that the ketones do start from 200. Right, last one. We've worked out the formula and we saw it's got a double bond there and it's not a carbonyl double bond. So we don't draw anything with a carbonyl double bond, it's got to be an alkene. So the same sort of thing, draw your 5 carbons in a row, start with, you can either start with the OH and then move the alkene double bond along, or you could start with the alkene and move the OH along. So here are some of the isomers. You could draw more, I just didn't have space to draw all of them. You don't have to draw all the isomers, as long as you can show what it probably is and some examples of what it couldn't be. They all have 5 carbon environments, and we do have 5 peaks in the NMR. And so we now have to use the NMR and the mass spec to work out what it could be. Remember I said we've got this wide gap between here, so it's a CH2. That means it's a terminal alkene. That, I know it's on the end, but it's not terminal. That OH will influence this quite badly and move it downfield, if you had that one. Okay, this is not terminal, so it's not this one. This is terminal, so it could be this one. This is terminal, it could be this one. Okay, that's terminal. So that's why I've drawn mainly the terminal ones. Now, why can't it be this one? We know from the NMR this is at 10. 10 is very upfield. It'll be a methyl group that's not being influenced by anything else. I do not have a methyl group here. I've got a CH2 with an OH on it. That is not going to ever give you a peak over there. It'll shift it down, and this one will be also downfield because it's being influenced by the O as well as being a CR2 peak. Okay, because the more carbons it's got substituted to it, the more downfield it is because it's more, or it's less shielded. Right, so these are 2 possible ones. The only difference is where the OH, how far down it is. So what we can try and do is use mass spec to see if we could perhaps separate between them. So this base peak at 57, it's possible with this one, which we've already agreed doesn't work from the NMR. It's possible with this one over here. So 57, remember, we've got to have three carbons plus 5 hydrogens plus 1 oxygen. You could also make it with more carbons, but we don't actually have enough carbons to make it sort of 57, so the oxygen must be present in that peak. So we know it's not carbon 1. We could make it carbon 5. Okay, so 3 carbons is 1, 2, 3 carbons. 5 hydrogens, 1, 2, 3, 4, 5. Does that work? Oh, no, it'll have to be broken the other way. 1, 2, 3 with a break over here. So that will add up to 57. So 1, 2, 3 carbons, 1, 2, 3, 4, 5 hydrogens, and the oxygen. So you've just put the positive charge there. It is a primary carbon, but remember, any oxygen close by will stabilize it, because the OH, the lone pair of electrons on the oxygen, will help stabilize that positive charge. And so that's why it's more likely to be this one than that one, because there's no ways I can get 3 carbons, 1 oxygen, and 5 hydrogens out of that one. If I break it at any of these points, it won't add up to 57. Any questions on that? No. Okay. I just want to check. Yep. So there I've just given another one at 29 if you were thinking of doing it. And again, it's 1 and 5. Right. So next week I'll definitely start with a 3061. And that's a solubility equilibria. And if you were choosing the fluoridation of water, then that's for your research topic. If you were going to be doing the 91389, then that would be a good one to do. Okay. Any questions before we close? No. Okay. You have a good day, and I hope you had a good break while you had your university. And I'll see you next week. I just see you typing. Right, not a problem. Okay, so just keep on sending that work in. Right, bye.